that when we talk about chemical reactions, one of the things you need to understand is that most times they can be represented by their chemical equations. They can be represented by their chemical equations involving symbols, involving formulas, involving symbols. Okay, we talk about water converting to ice. That's the liquid. We're talking about now under chemical reactions. There are some things we need to take notes. An example is reaction time. What is reaction time? Reaction time, please write, is the total time for a particular reaction to take place. Reaction time, reaction time is the total time for a particular reaction to take place. Okay, an example of such is if you are to boil your Indomie. God, do I know how many, do I know how many minutes it takes to boil Indomie? Okay, let me ask you, how many minutes does it take to boil your Indomie?
3 minutes.
3. Are you serious? 3?
Hmm?
Oh,
Yes.
wow. Maybe I should ask this question. Your Indomie, you like it dried or wet?
I don't like Indomie.
Sorry?
I don't like Indomie.
Oh, jeez. Okay, let's go to something you like, please. Spag.
Yes.
Okay, good. That's a neutral one. How many minutes does it take to boil your spag?
5 minutes.
5 minutes. Jeez. Okay. Okay. 5 minutes. Now the total reaction. Now, but do you understand that it's 5 minutes because you are using gas, isn't it?
Yes.
What if you are using stove?
The longer time.
It will take a longer time. What if you are using pressure cooker?
Let's take a shorter time.
A shorter time, maybe 2 minutes. Okay.
Yes.
Now, you see, there are different things that would determine a reaction. There are different things that will determine a reaction. That's why we say provided some things are made constant, because you just said 5 minutes because it was gas. What if it was stove? What if it was electric stove? What if it was pressure cooker? Now, that depends. So the reaction time for you might not be the same reaction time for another person, because time differs depending on what is a particular word there, temperature. We're going to come back to that later on. Okay, reaction, another keyword we want to define is reaction rate. Reaction rate. Now, what is reaction rate? Reaction rate is the number of moles of reactions. Reaction rate is the number of moles of reactions converted or product formed per unit time. Reaction rate is the number of moles of reaction converted or product formed per unit time. The number of moles of reactions converted or product formed per unit time. Now, this is very instructive because it has to do with the number of moles of what you have reacted. Now, that's a difference between reaction time and reaction rate. Reaction time is the total amount of time it takes for a reaction to take place. But reaction rate is the number of moles. When you talk about the rice or the spag, or okay, let's use the rice. When you boil your rice, at a particular time, not all the rice will be made, will be very soft to chew. Some will still be difficult, some will still be hard, one part will still be soft. So the number of moles, the number of all the things, of all the rice grains has been converted at a particular time, that is the reaction rate. But the total time when all of them becomes very easy for you to chew, that is your reaction time. Now, the unit of reaction rate is mole per mole dm cube, or mole per dm cube per second. Mole per dm cube per second. All right. Having understood this fact, having understood this fact, there's something I want to explain called activation energy. Now, in all chemical reactions, one thing we must understand is that we have some existing bonds in between the reactant particles, which must be broken before new bonds can be formed to form a product. Now, I want to ask you this question. Uh, let's use, we want to react some things now. Okay, we get our Indomie. The Indomie don't just start boiling. I mean, sorry, the spark. The spark doesn't just start boiling at that time. What happens is that it gets to a particular time, or a particular, it has to overcome some existing bonds, some energy. It has to break it down. And once that thing is breaking down, boom, new products are formed. Okay, let's use the burning of paper or the burning of a human being. Okay, the burning of a human being. If you're burning a human being, it's not immediately all the parts of the body will just get burned like that. While you're burning that person, a time comes he can't overcome it again. He just, oh, he cries, and that's the end. He just turns to probably a piece of bone or whatever. Now, the same thing with the same thing with breaking a solid. I mean, heating up a solid. The first time you're heating up the solid might not just melt. It might not just melt. It has to overcome a particular energy. It requires breaking of bonds, breaking the things, the intermolecular forces in between the solid, or in between the reactant particles. Now, an initial energy most times is required to activate the reactant particles. Now, the breaking of that energy, is what we call the activation energy. Activation energy. Now, when we talk about activation energy, now the activation energy most times of a reaction is equivalent to that energy barrier that must be overcome before bonds are broken to enable a reaction take place. Now, what is activation energy? Activation energy can be defined as the minimum amount of energy required for a reaction to occur. As a minimum amount of energy required for a reaction to occur. Now, when this activation is acquired by reactant particles, they form what we call complex particles of high energy content. Now, most times we call that the activated complex. Now, it's just, this is how it goes. The curve is just like, okay, um, let me see if I could give an example, just like a curve. Let's see. An example of what I'm saying is an example of what I'm saying is just as if it goes up, goes up, it goes up. Sorry about that. what's this? Now, this is something that explains what I'm trying to say is this. You are heating up a substance. The temperature keeps increasing. It keeps increasing. The moment it gets to this place, now this has to do with the activation energy. It has to be broken down. It has to be broken down to a part. The activation energy has to be broken down. And once it is broken down, then new products, this I'll call this the reactant and call this the product. New products are formed, but this activation energy must be overcome. It has to be, it's just like somebody climbing towards a mountain. It will be very difficult. Once the person gets to this place, it's the person climbing towards the mountain. By the time it gets to the next side of the mountain, you are seeing another side of the mountain. Okay, so but this has to be overcome. So this is the activation energy, and why the utmost part, we'll call that the activation complex. All right. Okay, now what do we mean by activated complex? Activated complex is an unstable molecule. Activated complex is an unstable molecule with high energy content, which gives the product. Activated complex, activated complex is an unstable molecule with high energy content, which gives the product. Now, it is actually unstable because of high energy content. So it's most times it will decompose to give the product or the reactant depending on the nature of the reaction. And now this brings me to what we call introduction. That's to the collision theory. Collision theory. Now, the collision theory was developed, that's from kinetic theory of gases, most times. And one of the postulates of the theory, we have about four postulates of the theory. Number one, let's write that down. Number one, okay, before we go into that, let me just show you a video on that, if possible. No, let's do this first. Let's do this first. Then I'll show you the video. Now, the theory, number one, that reaction occurs as a result of the collision of reactant particles. Number one, that reaction will occur as a result of the collision of reactant particles. No reaction will occur without collision. They have to collide. They have to collide. That is why we talked about
the collision of what?
Okay, collision of reactant particles. Collision of reactant particles. Have you written that?
Yes, sir.
Okay, number two, that a reaction results. A reaction results if only collision attains the minimum energy. If only collision attains a certain minimum energy. And I want to ask you, what is that minimum energy called? Remember I told you that reactions, they have to overcome a particular energy. They have to overcome a particular energy.
Activation energy.
Good. Activation energy. So a reaction will only occur if that collision has been able to overcome that minimum energy, which is called activation energy. All right, I guess you've gotten that. Okay, now the next one is a collision. Sorry, did you get the second one?
Yes, sir.
Okay, now the next one is collision will not give rise to a reaction. Collision will not give rise to a reaction unless the colliding particles are correctly oriented. Unless the colliding particles are correctly oriented towards one another. Unless the colliding particles are correctly oriented to one another. That means there's a place of orientation. There's a place of, that means they themselves, the particles on their own part, they must be perfectly oriented. If this is angle 90 and if one reaction is an angle 90, another one is probably on angle 180, that may not work. They have to be completely or correctly oriented towards each other. Number 4, which is the last one, that the rate of reaction is proportional to the number of effective collision. The rate of reaction is proportional to the number of effective collision. Now, a collision most times is said to be effective. Oh, I said the rate of reaction is proportional to the number of effective collision. A collision is said to be effective if the energy of the colliding particles is greater or equal to the activation energy. Please note that, very important, that a collision is said to be effective if the energy of the colliding particles must be greater than or equal to the activation and the molecules are correctly oriented towards one another.
Must be greater than or equal to.
Must be greater than or equal to the activation. That is activation energy. And the molecules are correctly oriented to one another. And the molecules are correctly oriented to one another. Now, this is very important that, remember we said something, that for chemical reaction to occur, number 1, there must be collision between the reactant particles. But it still doesn't stop there, that the rate of reaction is proportional to the number of effective collision. And it can only be effective, number 1, if the energy of those colliding particles, it must be greater than the activation energy. If it is not greater than the activation energy, there will be no products. There will be no reactions. All we just have is a normal reaction. Nothing is taking place. No new product is formed. That's why we start using that. Okay, how do we overcome activation energy? What are the things that could help us overcome activation energy? Wow, we now came to the sense that, number 1, there must be temperature. We must either increase the temperature or decrease the temperature. Why? Because temperature would make the collisions, make the number of effective collisions to be very fast. And once it is fast, what happens? The activation energy will be destroyed, either be destroyed or it has to be destroyed. It has to be overcome. Once it is overcome, new products can come in. Do you understand that?
Yes, sir.
Okay. Now, okay, let's go into, let me show you what I said I was going to show you then. Where is it? Come up. Okay. Where are you? Where are you now? Just come up. Are you seeing this, please?
Yes, sir.
Okay.
is and how to measure and calculate it. In this video, we'll look at the factors that affect the rate of reaction and why they affect it. Here are 5 factors that affect the rate of reaction. There's the concentration of reactants in solution, there's the pressure of reacting gases, the surface area of solid reactants. Now these 3 account for the 3 states of matter. So we have liquids, gases and solids. And then we have temperature. And lastly, we have the presence of catalysts. But before we look at these, we first need to understand how they affect the rate of reaction. And to do that, we need to understand collision theory and activation energy, because that explains how a reaction happens in the first place. A chemical reaction can only happen when reacting particles collide with each other. So if these are the 2 reactants, these 2 particles are the reacting particles, they need to collide in order to react with each other. The thing is, not every collision leads to a reaction. These particles, when they collide, need to have enough energy to cause a reaction. So they not only need to collide with each other, they need to have sufficient energy. And the minimum amount of energy that particles need to react is called the activation energy. So there are 2 ways that we can increase the rate of reaction. We can either increase the frequency of collisions, so more collisions, or we can increase the energy of the reacting particles. If we do either of these 2 things, or both, we can then increase the rate of reaction. So first, let's look at concentration and pressure. Increasing the concentration and increasing the pressure both lead to an increase in the frequency of collisions, because the particles are more crowded together. So let's take this as a container with some particles in it, the red particles and the green particles, which need to react with each other. If we increase the concentration so that it's more like this, then the particles are more likely to collide with each other and therefore react. And that's because they're just more crowded together. There are more particles in a given space. Alternatively, if we increase the pressure so that it looks like this, and here I've increased the pressure by making the container smaller, you can see that they are, again, more crowded together. So the frequency of collisions will increase. They are more likely to collide, and therefore the rate of reaction will increase. Increasing the surface area of a solid increases the frequency of collisions as well. And that's because there will be more surface area exposed. So let's take the example of this cube of material. If I split this cube in half, I have increased the surface area, because now there is this whole surface which is now exposed, and it's the same on this side of the other half. So splitting this cube in half hasn't changed the overall volume. The volume is still the same. I haven't added any material and I haven't taken away any material, but I have increased the surface area by cutting this cube in half, because I have been able to expose more of the surface of this material. And the more exposed surface area that you have, the more likely a collision can happen, because now there are more places for a collision to happen. There's a whole other surface here where things can collide with it. So by cutting it in half, I have increased its surface area to volume ratio, and that will increase the rate of reaction due to a higher frequency of collisions. So let's sum up where we are so far. We have covered the first 3, the concentration of reactants in solution, the pressure of reacting gases, and the surface area of solid reactants. Increasing any of these will lead to a higher frequency, so an increased frequency of collisions. If we we look at temperature, increasing the temperature does two things. One, it increases the frequency of collisions, and secondly, it increases the energy of the particles. So remember, if we think back to collision theory, you can increase the rate of reaction by increasing the number of collisions, or by increasing the energy of the reacting particles. And increasing the temperature does both. So we know already that if you increase the temperature of a substance, the particles will gain kinetic energy and they'll move around faster. So therefore, they are not only moving with more energy, but they are also more likely to collide. So last but not least, let's have a look at catalysts. We can sometimes use a catalyst to speed up a reaction. A catalyst is a substance that increases the rate of reaction without being affected chemically itself or without being used up itself during the reaction. Catalysts work by lowering the activation energy of a reaction. So let's look at this graph. The graph shows the activation energy of a reaction. We have the reactants to start off with, and at the end we have the products. And this blue curve shows how much activation energy the reaction needs in order to take place. So this blue arrow here shows us the activation energy for this reaction. Now we look at the pink curve, and this shows the activation energy when a catalyst is present. So basically, a catalyst will reduce the activation energy that is necessary for a reaction to take place. So to sum up, a catalyst reduces the activation energy. It reduces the activation energy necessary for a reaction to take place. So as long as we understand collision theory and what activation energy is, we can explain how each of these 5 factors actually affect the rate of reaction. The first 3 increase the frequency of collisions. Temperature affects both. It increases the frequency of collisions and it also increases the particle's energy. And catalysts reduce the activation energy needed so that more collisions will result in a reaction. Okay, so that was the factors affecting the rates of reaction. We also went over collision theory and what activation energy is. I hope you found this video useful.
Okay, these actually brings us to what we call the factors affecting the rates of chemical reaction. Wow, that was awesome. That was awesome. Okay, now we'll be coming into the factors affecting the rates of chemical reaction. I'm going to explain some of all those things that he just spoke about now. Can you hear me?
Yes, sir.
Okay. Number 1 factor is the nature of reactants. The nature of reactants. Now, most times the chemical nature of reactants taking place in a reaction would influence the rate of reaction. For instance, let me ask you this question. You've seen dilutes. You know the difference between concentrated acid and dilute acid, right?
Yes.
Have you seen a concentrated acid before?
No.
Okay, but this is okay. And so most of the examples of dilute acids, there are some acids that are not dangerous to us. Some examples such as citric acid. We take citric acid in our orange. We take citric acid. So most times we take them in. They have no effect on us. They have no effect on us. Good. Most times you also talk about we have acid from grape, from grape. They're not nothing is harming us. We are not being harmed by those kind of acids. But the game changer comes when we have concentrated tetraoxosulfate 6 acid or HCl acid. Now, if you put your hand, I've tried putting my hand in dilute acid, that's dilute HCl or dilute H2SO4, nothing. My hands were still, I could still feel the acid, I could still rub it, it was still cool. But the game changer came when mistakenly, I think that was by mistake because I wouldn't have done that on purpose, or um, I wanted to put my hand in concentrated acid. Jeez, the reaction was instant. I know I will first tried it. I first tried it then with paper. Tried it with other materials. I saw the reaction was instant. Was quite instant. Why? The nature of the reactant. The same thing also. When you bring iron, zinc, and gold metals, when you place them in different beakers and put hydrochloric acid, are you there? I was saying that when you put hydrochloric acid with zinc, normally it's meant to give you hydrogen gas. Hydrogen gas is meant to be evolved. Let's see the reaction. Hydrogen gas really is meant to be evolved because when acids are reacted with that's HCl plus zinc. When acids are reacted with zinc, it should actually give us zinc chloride and hydrogen gas. Hydrogen gas should be evolved. Okay, actually, that's what it should give us. But if it is a dilute acid, the rate at which hydrogen gas will be evolved will be slow. But when it is concentrated, when it's a concentrated acid, my God, the rate, what do you think will happen to the rate at which it should evolve? The rate will be what? Will be quite fast. Sometimes if it's a dilute acid, hydrogen gas might not even be evolved. It might be slow, it might be slower, or it might not even happen, or there might not be any reaction. But once it is a concentrated acid, the rate at which it would evolve will be quite faster. Will be quite fast. Why? Because of the nature of the reactant. So the nature of the reactant determines the rate of chemical reaction. Give us another example of such is wood. Bring wood and solid. When you want to burn wood and solid, a dry wood and a solid, the solid may not really burn. But the wood, because it is dried, will be faster. So the rate at which the reaction would take place will be very fast for wood compared to a solid, compared to a stone, compared to probably a solid thing. All right, so these are the difference. These are ways in which nature of reactants affects the rates of chemical reaction. Do you understand that?
Yes, sir.
Okay. That's cool. The next one is effect of concentration. Concentration, we can also call it the pressure of reactants. The pressure of reactants. Now, I want to say this, that when reactant particles are crowded in a particular place, the frequency of collision will be faster than if the particles were far apart. Now, what do I mean? Bring 100 human beings into a small room. bring 100 human beings into a small room, what would happen? There would be, when 100 human beings are being brought into a small room, one of the things we will notice is that their collision, the frequency of collision will be faster than if they were far apart. Now, bring 100 persons into a small room, and probably somebody decides to fart inside that small room. Geez, that would be a living hell for them. The same thing, bring 100 persons into a small room and let somebody come in, spray an air freshener or a perfume. The frequency of diffusion would be will be faster than if they were far apart. Now, this tells us that the more the concentration of a reactant particles, please write this, the more the concentration of a reactant particles, the higher the rate of reaction. The more the concentration of reactant particles, the higher the rate of reaction. Now, when we talk about pressure, the effect of pressure on the rate of chemical reaction, please write this, note that pressure affects the concentration of gaseous reactants. Pressure affects the concentration of gaseous reactant. What do I mean? What I mean is this: the higher the pressure, the higher the pressure, the higher the frequency of collision. The higher the pressure, the higher the frequency of collision. The higher the pressure, the higher the frequency of collision of the particles, and the higher the rates of reaction. What I said was this, that pressure affects the concentration of gaseous reactants. And I said that the higher the pressure of gaseous reactants, the higher the frequency of collision, and thus the higher the rates of reaction. Did you get that?
Yes, sir.
Okay. Now, what does this tell us? That pressure affects only what? Solid, liquid, or gas?
Solid.
Sorry?
Gas.
Gases. Now, they might twist you and ask you, they give you a reaction in solids, and they're going to show you, if they want to ask you this kind of technical question, they're going to ask you, that's tricky question, not really technical. They'll give you questions that has to involve solid. They'll show you the solid sign, they show you the liquid sign, they now ask you, what is the effect of pressure on this? Come on, what is the effect of pressure on this? Pressure has no effect. Pressure can only have effects when that reaction or those reactants are gases. So note that that's quite instructive, very, very important for us to note. That pressure would only affect it if it's in the gas medium. But if it's in solid medium, pressure has no way. Pressure cannot affect that. Do you understand that, please?
Yes.
Okay. 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 Now let's look at the next one is the effect of surface area. Effect of surface area. Effect of surface area. I want to ask you this question. Okay, let's bring, for example, let's assume we want to heat up a stone, a big stone, and we're heating up the big stone, but somebody decides that, okay, I don't want to heat up my big stone first. The first thing I do, I will break this stone. He breaks up the stone, makes it some of them small, make them small, very small, and decides that, okay, all those small pieces of the stone, he decides to heat it. Both of them decides to hit the stone at the same time. This guy is a big stone, this one is a small stone. He has broken his bigger stone into pieces and begins to hit them. Which one do you think would break more? The bigger one, or the one with the big stone, or the one that has broken his big stone into smaller pieces?
One with the big stone.
Which one do you think they would hit more? Like we decide, okay, this guy with the bigger stone decides to, this guy with the bigger stone decides to heat up his own, maybe using a whatever, gas, fire, whatever, heat it up. Now this guy comes with his own smaller stone, decides to heat up. Which one do you think would hit more? Like would be broken into pieces later on again? The one with the big stone or the one with the smaller stone?
Smaller stone.
Why?
Because it's already small and broken down, so it will be easier for the
Good. That's exactly, that explains surface area example. Now, please write this. The more exposed the area of contact of a reacting particles, the more exposed the area of contact of a reacting particles to each other, the more exposed the area of contact of reacting particles to each other, the faster the rates of reaction. The faster the rates of reaction. Okay, now let me come back to our noodles. Indomie, or sorry, spag. Cool. Okay, let's come to our spag. I don't like spag, but you like spag. I think I prefer Indomie to spag. Now, then but if I want to cook spag, I hate breaking it down. I like it being very long. So you just take it, just suck it in, boom. I like that. That's if I'm going to eat it. Now, but I discovered then that I would not break it down. And so it took longer time for it to boil. Maybe if it was meant for 5, okay, when you cook yours, do you break it? Do you break it like into, I was explaining that I like taking spark. No, I didn't like taking spark. Then when I used to take, when I want to take spark, I like making it so, I don't like breaking it. But I noticed later on that anybody who breaks his spark, maybe shreds it into, or most times, if you try shredding your spag into pieces before putting it into the hot water or whatever, you will notice that if you're very, very observant with your time, you will notice that the time it took for that spag when you did not shred it or when you did not break it, it's the time it took for that when you shred it, the time will be faster, will be smaller, sorry, compared to when you did not shred it. Why? Because when it was not shredded, when you did not break it, the heat, the energy has to overcome the activation energy. The temperature has to overcome the activation energy of breaking the spark and now boiling it for you and probably drying the water. But since you have already shredded it, good. There's no more energy to overcome there's no more temperature. The temperature would no more overcome any activation energy. All you just need to do is help you cook it and help you dry it. So the more exposed the area of contact of reacting particles to each other, the faster the rate of chemical reaction. Now, I just told you that for solid reactants, exposed area must be increased by subdividing or breaking the solid into smaller pieces. When it's broken into smaller pieces, then the rate of reaction will be faster. But what happens when the reactants are gases, liquids, or solid dissolved in solution? What we'll do is this, that the mixing of, the thoroughness of mixing these things are very, very important. That's why when you take your tea, when you take your tea, you turn it, you mix it very well to ensure maximum contact between the reactants. You must mix them very well. When you mix them very well, when you mix them properly and very well, you will notice that the rate of reaction would be faster for gases, for liquids, or solid dissolved in solution. Okay, the next thing we want to talk about is effect of the presence of light. That's light. 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 Now, when we talk about light, there are some reactions that are affected by light, and these reactions are called photochemical reactions. Photochemical reactions. That means photo means light. That means they are reactions that are affected by light. Now, they are thus to overcome the activation energy barrier and react rapidly by chain reaction. That is the reason why, or this is the reason in your lab, when you want to, if you check how silver halides, like silver chloride, is being stored. Silver chloride is not stored as other plastic, it's not stored in a transparent bottle. When you go to your lab, have you noticed that chemistry lab, that most times stuff like silver chloride, they are not stored in a transparent bottle. Rather, they are stored in a dark colored bottles called amber bottles. Why are they stored in amber bottles? They are stored in amber bottles because silver chloride is a photochemical substance. It can react with light. Once light, probably light, maybe the light of your bulb, the light from the sun, shines on silver chloride, reaction takes place. Reactions start occurring, even in the bottle. That's so because of that, silver chloride, a very good chemist in a very good lab, would not store silver chloride in a bottle, in a transparent bottle. Rather, they go for amber bottles, a dark colored bottles to store your silver chloride. Do you have hydrogen peroxide in your house?
No,
Have you seen hydrogen peroxide before?
I think so.
Okay. Have you noticed that it is not stored in a transparent bottle? The bottles of hydrogen peroxide most sometimes are dark colored bottles. They are amber bottles. So that's because it's a photochemical compound. It can react with light. Okay, now the presence of light can also affect. Now, I just gave you two. Number one, the composition of hydrogen peroxide. Number two, the conversion of silver halides. An example is silver chloride. If silver chloride, the conversion of silver chloride to gray metallic silver. All right. Now the next one, okay, let me give you three. Reaction between methane and chlorine. Reaction between methane and chlorine. This happens under the presence of ultraviolet light. Methane and chlorine. The reaction will keep going on. We keep going on. Oh, we've not gone deeper into organic chemistry. That's why it takes place. That's this is sometimes it's called chlorination. It's sometimes also called substitution reaction. In ultraviolet light, the reaction keeps going on, keep going on, keep going on until until the hydrogen atoms in methane is being used up by chlorine. Okay, the next one is the effect of temperature. That is very awesome. That's awesome. Effect of temperature. I like this part. Please write this. The higher the temperature, what will happen to the rate of chemical reaction? Will it be high or will it be low? The higher the
High.
temperature, good. So complete it. I will not complete that part for you. The higher the temperature, the dash rate of reaction. The higher the temperature,
Yes.
dash the
The
rate of,
faster the rate of reaction.
sorry?
The faster the rate of reaction.
Okay. The higher the temperature, the higher or the faster the rate of chemical reaction. Now we know that when the temperature of a chemical reaction is increased, the number of particles with energy will become equal or greater than the activation energy. So it becomes increased. The kinetic energy of the reactant particles increase, and this increases the number of effective collision. That's one reason why pressure cooker will still be faster than gas, because it increases. It's just like you just set everyone on your mat, get set, go. You just set up everyone on fire. So there's increase in the frequency of effective collision, and therefore increase in the rate of reaction. So temperature has a very, very good way of affecting that. Okay, and the last one we'll be looking at is catalyst, the effects of catalyst. Now, what is a catalyst? A catalyst is a substance. Oh, sorry, let me ask you, maybe you have an idea. What's a catalyst?
Um, a catalyst is a substance that increases the rate of reaction without losing anything of its own.
Good, that's exactly what I want to hear. And you fell into my trap. Good. A catalyst will not only increase, a catalyst also decrease the rate of reaction. A catalyst is a substance that alters is a better way to put that. A catalyst is a substance that alters the rate of chemical reaction. It doesn't just increase the rate of chemical reaction, it also has the capability. We also have catalysts that decreases. The catalysts that increase the rate of chemical reactions are called the positive catalyst. That's catalysts that speed up the rate of reaction. Now, what happens when we have a positive catalyst? What happens when we have a positive catalyst? Let's see something. Let's see something. Okay. Let's have this. Let's have this. Good. Wow, that was bad. Let me manage this, please. No, no, no. Wow, finally. We'll call this reactant. Let's call this the product let's call why am I using black only? Come on, make it colorful. Okay. Okay. Let's call this is the activation energy. Okay. The activation energy, the energy that must be overcome. Right. Now, this is what a catalyst does. This is exactly what a catalyst does. Remember, this is the activation energy, the energy barrier that must be overcome. That's, I call it activation energy. Now, this is what a catalyst does. That's a positive catalyst. Remember, it has to speed up the rate. It has to speed up the rate of chemical reaction. So this is exactly what it does. It reduces. This is exactly what it does. It reduces the activation energy. So instead of the reaction going through this whole process of climbing this mountain, oh, the catalyst just brings up a shortcut. Don't worry, I'm going to help you. That's the same thing like the grace of God coming upon somebody. The grace of God just coming upon someone. Instead of the person going through these years of hard work, the person's journey is just shortened. The catalyst just reduces the rates. That the catalyst just reduces or lowers the activation energy of the reactant particles. Please, that's a very key thing you should write. That the positive catalyst lowers the activation energy of the reactant particles by providing an alternative pathway so that the reactants this time can collide effectively to produce more product. So exactly what it does, the activation energy. Now, this becomes, at this stage, now this, at this stage now, this becomes activation energy. Okay. Now, this is also an activation energy. This is also activation energy, but this is activation energy with catalyst. We call that EA. Activation energy now with a catalyst. This is an activation energy with a catalyst. That the catalyst just shortens the distance of how much the product can be given up or we can produce it. So that just shortens the distance. So note, a positive catalyst lowers the activation energy of reactant particles by providing an alternative pathway so that reactant particles are able to collide effectively to produce more products. Now, examples of these catalysts we have, it's manganese 4 oxide, MnO2. Manganese 4 oxide. Manganese 4 oxide is actually used in the production of oxygen. It's used as a catalyst in the production of oxygen by thermal decomposition of ClO3. That's potassium trioxochlorate 5. Now, manganese 4 oxide. Now, I want to ask you, if this is what positive catalyst does, What would happen to negative catalysts?
They'll increase.
Sorry?
They'll increase
Good. They will increase the what?
activation.
They will increase the what?
Activation energy.
Good. Increase the activation energy. Rather, this is exactly what we're having. We're having, wow, something very big. They'll be having something very big. So a negative catalyst will just increase the rates, increase the activation energy, while a positive catalyst lowers the activation energy. Okay, I guess I have some things to show you which I have not showed you. Okay, I think I have just 2 more videos to show you which I have not showed you. Okay, are you seeing this?
Yes, sir.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation.
I guess you remember that, correct orientation. You remember that, right?
Yes, sir. Huh? What's thinking?
That allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I proposed 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I proposed that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and
Tell me, this is quite funny. Tell me, okay, what are they trying to do now with what I've explained to you now? What are they trying to do?
Yeah. Tries to show
Remember, actually, this is what happened. The place was wide. Now he decided to shrink the size together so that, you know, if they were far apart, now they will start coming together and they'll start colliding to, okay, this is the love. This is my own love. This is my own love. All right. So what does that explain in I think I explained something like that also. I explained
Is that it
so what was that?
increase the as you're shrinking the building, it was now making the energy as they used to collide increase.
Okay, so which of the factors of rate of chemical reaction is this now? Which of the factors is it trying to do now? Are we trying to explain here?
Catalyst.
Sorry?
Effects of catalyst.
No, this is not catalyst.
Okay, pressure.
Pressure, correct. This is actually pressure. Remember I said when we shrink them together, there will be more pressure. So exactly what is happening here now. Okay, let's continue.
Enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together, and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we
Okay, which is this one now? Is that increasing the total population of the school? Increasing the total population of the school. That means we have many students now. Which factor is this?
Surface area.
Is it surface area? We could also call it the nature of reactants. Now we have more reactants or more concentrated reactants in this case. All right, let's continue.
create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs,
What does this explain? Which factor? Okay, maybe we should.
Concentration of reactants.
Sorry?
Concentration of reactants in solution.
Maybe you get it more.
outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has some more area exposed that is
surface area.
Okay.
available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and
What is the matchmaker?
Catalyst.
Catalyst.
dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing two particles together and orienting them correctly in space so that the two can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
Okay, that was quite good. Awesome. Okay, I think I have one more before I think I have one more. Let's see. Okay. This is it. Is it this? Let me see. Oh god, I should have. Okay, this is just for some few minutes. Okay, okay. I have good questions waiting for you here.
In today's video, we're going to look at the factors that affect the rate of chemical reactions. So temperature, concentration or pressure, surface area, and the presence or absence of a catalyst. Before we can understand how these factors affect the rate though, we need to cover the theory behind reactions, which is known as collision theory. This states that in order for particles to react, they have to collide with each other with sufficient energy, which we call the activation energy. And if they collide with less energy than this, then nothing will happen. They'll just bounce apart again. So if we were to think about an entire reaction, which will involve tons of particles, then the rate at any particular point is going to depend on two main things. The most obvious is the amount of energy that the particles have. The more energy they have, the more energy they can transfer during the collision, and so the more likely they are to surpass that minimum activation energy. The other important thing is the frequency of the collisions, which just means how often the particles collide with each other. So even though not all collisions are successful, because the particles involved don't always reach activation energy, the more often they collide, the more successful collisions there'll be overall. Now, whenever you think about how these four factors affect the rate of reaction, you always want to think in terms of how they affect the amount of energy that the particles have and the frequency of the collisions, as increasing either of these will increase the rate of reaction by increasing the number of successful collisions. Let's start with temperature. As the temperature of a reaction increases, the particles gain more energy, which means that they move faster. And because they're moving faster, they'll collide more frequently. They'll also collide with more energy each time, so are more likely to exceed the activation energy. So overall, there will be a higher rate of successful collisions, and thus a higher rate of reaction. Now, concentration and pressure are normally considered as a single factor, because they both refer to how many particles there are per unit of volume. It's just that concentration generally refers to solutions, and pressure refers to gases. When either of these is increased, it means that there'll be more particles per unit of volume, which makes the collisions more frequent, and so it increases the rate of reaction. Just like concentration and pressure, a higher surface area will also increase the rate of reaction. For example, if we wanted to react 3 grams of magnesium with an acid, we could use a solid block of magnesium, small chunks of magnesium, or powder. As all of these have the same mass and volume, the powdered form would have the highest surface area to volume ratio, and so would have a much higher area over which collisions with the other reactants, in this case the acid, could take place, meaning that the frequency of the collisions would be higher, leading to a higher rate of reaction. The last factor that we need to cover is the presence of a catalyst. Catalysts are substances that speed up a reaction without being used up in the reaction themselves. So we don't include them in the reaction equation, as they're not reactants or products. To understand how they work, we can use a reaction profile, which shows the change in the chemical's energy during a reaction. Now, this distance between the reactant's energy level and the very top of the curve is the activation energy, which, remember, is the energy that the collisions have to have before they can react successfully. What a catalyst does is lowers this activation energy by providing an alternative reaction pathway. And this means that there'll be a higher proportion of successful collisions. The word catalyst is actually a pretty broad term, and a whole range of different substances can act as catalysts in different situations. One of the most common sources of catalysts, though, are the transition metals, like cobalt and nickel. And if you do biology, you'll have come across them in the form of enzymes, which are just catalysts made by living organisms. Anyway, that's all for this.
Okay, I guess this was a bit boring, but nevertheless, you understand everything now because we've done the other ones before. We've been able to explain all these concepts in the other one. So this was not, yes, it would have been boring if I played this first, but I guess you understand most of what was said, right?
Yes.
Okay. I'm actually looking for, okay, I guess, what else again? Okay, our next class we'll be looking at types of reactions. We have endothermic and exothermic reactions. We'll be going into them in full force. All right, let's see, can we answer some questions? Oh no, the question, okay. Okay, let me see. Okay, this is a question. Let me see if I could send it to you. Send the question to you. Now, which of the following statements is not true about the reaction between dilute hydrochloric acid and marble chips, calcium triisocarbonate? It is faster than 3 seconds. No, we don't need this question now. When we're done. It's a particular question that comes in mind right now. Okay, first assignment, number 1, it's explain endothermic reaction. Endothermic reaction. And the next one is explain exothermic reaction. All right. With the aid of a diagram also. Use a diagram. Number 2. Number 2. Write a relevant equation to show the industrial process in which vanadium 5 oxide was used as a catalyst. Write a relevant equation to show the industrial process in which vanadium 5 oxide, V2O5, was used as a catalyst. Gotten that right?
Yes, sir.
Okay, that's awesome. I'm looking out for more. Oh God. And the last question is states Le Chatelier's principle. States don't worry, Le Chatelier's principle. Okay, so the first one is explain endothermic reaction, exothermic reaction using a diagram also. relevant diagrams will be important. Write a relevant equation to show the industrial process in which vanadium 5 oxide was used as a catalyst, and Le Chatelier's principle. All right, that's where we'll be stopping for today. Tomorrow will be on physics. Let's pray, please. Any question?
No.
All right, let's pray. Father, we thank you for today, for your mercies. Thank you for your love. Blessed be your holy name in the name of Jesus.
Amen.
We thank you for your wisdom. Thank you for everything. Thank you for great things you're doing through the life of your daughter. In Jesus' name I pray.
Amen.
All right. Have a wonderful time.